All right, welcome and good evening, everybody. Please take your seats so we can get started. As usual, we'll start with a quick organizational remark. First of all, on our Moodle page, we now have a quiz for you that is available. So you're invited to take that quiz. It covers lots of topics that we have discussed during this linear algebra part, including the topics that we will discuss today, or some of those. If you can, it would be good if you could try to take it until Monday, 10 o'clock. I will then take a look at the results that we have so far to determine which questions to discuss with priority in class next week. Of course, if there are any questions that you'd like to ask, whether they are connected to the quiz or not, feel free to post them to the tweetback page for week 9. That is also already open and the link is on the Moodle page. All right. Then let's quickly talk about orthonormal bases and Gram-Schmidt's method. Here's a quick warm-up question. You will remember Gram-Schmidt's method. We basically quickly discussed that yesterday. We'll see some examples today. As a warm-up question, what I'd like to know is when I apply Gram-Schmidt's method, is the order of the basis vectors important for the result, or will the result always be the same? So I'll start with the same basis, I just change the order of the vectors. Will that influence the result? Is that true or false? Let's see if you can answer that, if that works. See if I can start that. Just a second. Somehow my connection doesn't seem to work reliably today. Now, quiz should be online. Let's take 30 more seconds. All right, time's up. Let's take a look at the results. Try one more time. Here we are. So almost a tie. A little more false votes than true votes. And as always, the majority is right. The answer is false. Maybe let's discuss this when we see an example for Gram-Schmidt's method. All right, so before we move on, let's discuss Gram-Schmidt's method once again. And then we'll take a look at an example. So once again, the idea is we have a vector space, we have a basis for that vector space, and we want an orthonormal basis for that same vector space. And of course, we need a scalar product for that. And Gram-Schmidt's method is then a way to obtain that orthonormal base. It works in iterations. First, we start with the first basis vector of a given basis, and we just normalize that to start off, right? So that's our B1. And then we do the following. For our second vector, V2, we compute the projection of V2 onto the space spanned by B1. Right? So we have this B1 vector here. So that is B1. Then the space spanned by B1 is that. Right? So here's the vector. Here's the space. And we have our V2 vector that might look something like this. And what we do then is we compute the projection of V2 onto that space that is spanned by B1. So what that means is basically we write this V2 vector, this red one here, as a sum of one vector that is in that space and one vector that is orthogonal to that space. Right? So this here, this is our projection. And this vector here, this is V2 minus the projection. So that is, maybe let me use another color for that. That is exactly the vector that we want to obtain. That is, in simple words, the part of V2 that is orthogonal to the space spanned by B1. Right? So that's what V2 adds to the information that is already given by B1 in a certain way. Right? We take out everything that already covered by B1, and that is the remainder. And that will be our second basis vector of the O and B. Right? Now we have two orthogonal vectors. They span the same space that V1 and V2 have spanned, but now they are orthogonal. And of course, we need to normalize that afterwards. And then we go on in the same way. So the next step, we take our V3, we compute, again, a decomposition of V3 into one part that is in the plane spanned by B1 and B2, and one part orthogonal to that. Right? So let me see if I can do something like a sketch. So here we have this plane here that is spanned by our vectors B1 and B2, and those are orthogonal. And then we have another vector, V3, that points outside that plane. And what happens is, again, we compute a decomposition into an orthogonal part and a part that is inside of that plane. And the interesting part is this vector that is orthogonal to the plane. That's the part that we still need to obtain the same space that V1, V2, V3 have spanned. So we need to add that to our B1, B2 to obtain the same space, right? The rest is, so this blue part here, that is in a way already covered by what B1 and B2 can do. We're only interested in the part that's not covered by B1 and B2. Okay, so that's the next vector that we get. And again, we normalize that. And again, we just continue with this until we have exhausted our basis. And of course, for this projection step, what we actually do is we compute the projection onto B1 and the projection onto B2, and then we just add those up. So this is where this sum here comes from. It's just adding up all these projections on the axis that we already have. Okay, that's the basic idea of Gram-Schmidt's method. And for that method to work, it is absolutely essential to have these vectors here normalized. In some of the books, you will find versions where, oops, maybe a little thinner, where this looks like this. So you add normalization in that step. And of course, you can do that. In the end, you would then obtain an orthogonal basis, and you would afterwards have to normalize that if you want an ONB. The downside of this is that you have to do this normalization in every step again and again and again. And that's the reason why I always do that before I go on to the next step, right? So I normalize every time to make sure I always have the right vector here, and I only need to do it once. And you need that normalization so that the computation is correct. Otherwise, you won't get the correct projection. So even if you just want an orthogonal basis, even if you don't want a normalized basis, you still have to normalize in all the intermediate steps. Only thing you can ignore is the last vector. Yeah, if you don't want a normalization, the last vector, of course, doesn't have to be normalized because you don't need that for any more computations, but that's it. Any other vector needs to be normalized, and you either do it inside the formula every time, and then 50% of the time you get it wrong, or you just do it once. Okay, and that's why I introduced that normalization in each and every step. All right, so that's the theory. Quick example. So here's a vector space. Consider that vector space U spanned by those two vectors. That's a subspace of R3. So what we have here is a plane in three-dimensional space. And we want an U ONB of U. Let's concentrate on that part first. Yeah, just U. We start with this vector B1. We normalize it. The norm of this is square root of 2, so we divide that by square root of 2. This is the normalized version of B1. Next, we compute B2 prime. That's the not normalized version of B2 by taking this V2 here and subtracting the projection of V2 onto the B1 space. Right? And we get that. Remember, we need to use the normalized version here and here. Here's our V2. Here's our V2. And then we just go through the computations, right? The normalization factor appears here and here, so you have that twice. And remember, by bilinearity of the scalar product, you can take that out. And that means I have those two normalization vectors here, and that way I get rid of the square root. 1 over square root of 2 times 1 over square root of 2, that's just 1 over 2. Yeah, so that looks a little nicer. Don't forget to do that before you do these computations here. That makes things a little nicer. All right, then I compute the scalar product. That is 2. So what I get is V2 minus 1, 0, 1. And you can see this is the part of V2 in a way that is inside that B1 space. That means it's parallel to B1, of course. And in this case, it's even almost the same vector. The length doesn't quite fit, but that's it. Right, that's the result. So this vector should be orthogonal to 1, 0, 1. And if you just do the computations quickly, you'll see this is, well, scalar product is 1 plus 0 minus 1. So that seems to be correct. Always a quick check you can do. And then all that's left is to normalize that. And the norm of that is, well, square root of 1 plus 4 plus 1. So 1 plus 4 plus 1, that's 6. So the length is square root of 6. And that means to normalize it, we just divide by that length. So here we have our orthonormal base for U. All right, and what you can see is this direction, that's the first one that we used, that also appears in the ONB. This direction here does not appear in the ONB anymore, right? So that is still here. That's a completely different direction. So what if we had started with V2 instead of V1? Well, if we would do that, the first step would be to normalize this vector, and that would be our first basis vector. Right? And hopefully you can see that a vector that is the normalized or scaled version of this one doesn't show up in this basis here, but it would show up if we had started with that vector. So the results are in fact different, and they depend on the order of the vectors. That was a question, I think? Yeah? Right, so the question is, the span of those two vectors are the same, right? So the span is independent of the order that we're using, that's correct. But the vectors themselves would be different, so we would get a different basis but for the same vector space, of course. All right, so that is Gram-Schmidt's method. Any questions so far? Otherwise, before we go on, I think I'll let you practice a little. I did prepare an example here. So here is a vector space spanned by 3 vectors in R⁴ to make things a little more interesting. And your task is to determine an orthonormal base of this subspace V here. Sure? Mm-hmm. So the question is about the order of the vectors in the basis, right? Okay, so as I said, for the result, it doesn't really matter which order you use. You can choose that freely. Right? The vector space spanned by the basis that you obtain will always be the same. The basis you get will be different, but it will do the same thing. It will be orthogonal, it will be normalized, it will span the same space. So basically you can choose whatever vector you want to start with. You can choose which order you want. The results will be different, but they will still be correct. Yeah? And if there is a clever way, a clever order of doing that, of course, you're free to choose that. Right, maybe one more thing before you start. Please briefly stop after you have obtained the first vector so we can check if you're right. There is a quiz that I've prepared on that, and it starts right away. And here's 4 possibilities for that first vector. I write down the basis on the bottom of that page so that you have that as a reference. Just a second. And of course, these answers assume that you actually start with the first vector of my base. So that will be the preferred order now. All right, let's quickly check whether you're correct before you move on. I'll give you 20 more seconds to log in your answer. All right, Let's see if I can display that. Great. So most of you answered C, which is this vector here. And of course you are correct. That is the normalized version of a first basis vector. So let's go on with vector number 2. I'm sorry, TweetBack seems to behave strangely today. So now we have both questions open. Concentrate on the second vector, please. Just a quick show of hands. Who's done with the second vector? Who needs some more time? Good, so we'll take a few more. So maybe one more minute. Sorry? Do we divide by 1/2? So you're saying my answers are wrong? But that's totally possible. I don't claim that's all correct. Let's see what the results are, and then maybe we can discuss your approach. All right, time's up. So let's see if we can take a look at the results. Here they are. So most of you claim that B is the right answer, and as usual, most of you are correct. That should be the correct answer. Should we do that step together? Anyone else wants to see that? Okay, so let's quickly have a look at that second step before I let you do the third one. All right, so once again, let me just copy this here as a reference. Just a second. And then we'll also see whether my results are actually correct. Okay, remember we started with this vector, we normalized that, and because the question came up, normalize just means divide by the length of the vector, so that the resulting vector has length 1. That is what normalize means, right? So that means our B1 here, the first basis vector for the O and B, that was 1 over the square root of 2 times 1, 1, 0, 0, right? Because the length of this here is square root of 2. So by dividing over that, I get a vector that has a length of 1. Okay? So that was my first basis vector. Now for the second basis vector, was step 1, here's step 2. I first compute the non-normalized version of my second basis vector. And I get that by taking the original second vector, this one here, 2, 1, 0, 2. And then I subtract the projection of that vector onto the space spanned by the first one, or in general by what I already have. Right, and that projection, that is given by the scalar product of this vector here. and my B1. And then multiplied by B1. And remember, we need to use the normalized versions here, right? So this 1 over square root of 2 factor, this is essential. Otherwise, you'll get wrong results. Okay, so let's do the computations. Just copy the first part here. Then I'll take those two, I'll take those two factors here. I can take that out of the scalar product, and I can take that to the front. So together, I'll get 1 over square root of 2 times 1 over square root of 2, which is 1/2, to make things a little simpler. Times, let me just write that once again to make sure you all get that intermediate step here, times this, this scalar product times the vector. Right? So now the normalization factors have moved here, and that's all that has happened in that step. So I need more pages. Oops. Okay, now next I'll just compute the scalar product. And I'll say this is 1 over 2 as a factor. The scalar product of those two vectors is, let's see, 2 times 1. 2 times 1 plus 1 times 1 plus 0 plus 0 times this vector, 1, 1, 0, 0. All right, so what I get here, 2, 1, 0, 2 minus, let's see, 2 plus 1 is 3, so I have 3 over 2 times 1, 1, 0, 0. And now we'll see if I'm correct. So 2 minus 3 over 2, that's 4 over 2 minus 3 over 2 should be 1 over 2. 1 minus 3 over 2 should be minus 1 over 2. Then 0 minus 0 is 0. And finally, 2 minus 0 is 2. Right? So this vector should now be orthogonal to B1. Let's briefly check that. Oops. So the scalar product of my B1, and now the normalization doesn't matter for the scalar product here, because it should be 0 anyway, so the factor is not really relevant if I'm correct. And if it's not 0, then something is off, so I have to double check anyway. And that is obviously, well, 1/2 minus 1/2, and the rest is zeros. So that's 0, as it should be. Right, so my vector is orthogonal, and now all I have to do is normalize. And that means I have to compute the norm of B2 prime. And the norm is, let's see, the square root of 1/2 squared plus minus 1/2 squared plus 0 plus 2 squared. Whoop. So that is the square root of 1/4, and 1/4, that's 2/4, or 1 over 2, plus 4. 4 is 8/4, 8 over 2, so I get 9 over 2. And the square root of 9 is 3, so I get 3 times 1 over the square root of 2, right? And now all I have to do is set B2 to B2 prime divided by the norm of B2 prime. So that is, let's see, square root of 2 over 3 times that vector that I got here, 1 over 2 minus 1 over 2, 0, 2. And to make that a little nicer, maybe let's take out that factor 1 over 2 here, so I don't have to write it that small. So we get that times 1 over 2 times 1 minus 1, 0, and 4. And then finally, square root of 2 divided by 2 is 1 divided by square root of 2. So 1 over 3, square root of 2, 1 minus 1, 0, 4. And that is hopefully the result that I claimed, is it? Okay, so maybe you got stuck somewhere here. Of course, that is also a valid result, right? You could just keep it that way. That's fine. I just want to get confused with those 1 over 2's in the vector. That makes things awfully hard to write, so that's why I'm taking out that factor here, and I arrive at that. Any questions about this? Great, and then let's do vector number 3 then. And here's again the possible answers, and let me again copy that V here for you. And let me again start a quiz. And then finally, I would be interested in how difficult you would rate that problem. So there's another question asking for that, if I can get it started. Get a quick show of hands. Does anyone have a result already? Okay, that's not very many yet, so let's wait a few more minutes. So let's say we take 1 more minute, and we'll see what your results are. All right, time's up. So here's your votes. About 60% of you seem to be sure that A is the right answer, and you are correct. A is the right answer. So this is the vector that you should have obtained. And also, let's take a quick look at the difficulty rating, if I can get that to work. doesn't seem I can get it to work. Now let me just tell you, so most of you, well, not quite what I was expecting. Most of you seem to think this is a rather hard problem. There were also quite a few votes on the easy side. And I would hope that, now it is, I would hope that once you get acquainted to this type of problem, you will actually agree with me that this should be a fairly easy problem. Of course, you need to pay attention to not make any mistakes. Computations are not always nice because of this normalization thing. You need to deal with a couple of square roots usually. But basically that's it. It's always the same recipe. So if you just follow that, there's not a lot you can do wrong. Once, as I said, once you get a little routine in that. Yes? Yeah, I was just going to ask that. So let's do that second step. Let me just write down what we have achieved so far. So remember, B1 was 1 over square root of 2, 1, 1, 0, 0. And B2 was, let's see, 1 over 3 square root of 2, 1, minus 1, 0, and 4. And now for B3, again, I'll start with the non-normalized version. And I get that by taking this third vector here, so my third basis vector, 1, 0, 1, minus 1. And now I subtract the projections of that vector onto the B1 and onto the B2 axis, so on the space that they span. And I do that as before by computing the scalar product of that vector with first B1 and multiply that by B1. And again, remember we need to use the normalized versions here, so that factor is essential. And then I'll do the same thing with B2. Right, so I compute the scalar product with B2 now. Yeah, almost the same term, just changing that second vector here, 1, minus 1, 0, 4. All right, and the result will then be a vector that should be orthogonal to both B1 and B2. Okay, let's do the computations. So once again, the question has been asked, what was I doing with these two factors, just taking them out here? So let me just elaborate on that briefly. Basically what I'm using here is one of the properties of the scalar product. You will remember that, or hopefully you will remember, that for a scalar product of two vectors v and w, if we scale this w by some scalar lambda, then we can take that out. Right, so this is the same as taking out the lambda. We can take out scalars of that, scalar product if we keep one of the parts as they are. So in this case, the v stays a v, right? So only do that one at a time. We could also do that in the first factor if we keep the second one constant. Works for both factors. And that's why I can take scalars out of the scalar product. Sounds a little strange if I say it that way. Yeah, but that's what I'm using here. So this here is a scalar, a real number, and I can take that out of the scalar product. And of course, this is also a real number. So here, the result of the scalar product is a real number. This is a real number, so I can change those any way I want. And that means I can also take this to the front and move those two together, and that way I'll get rid of the square root, because I just have that factor twice. Okay, so what's what I'm doing here? Let me just write that once again. So here we have that factor 1 over square root of 2, 2 times. Then we have this scalar product of the vectors now without that scalar factor, and here again I have moved that scalar factor somewhere else. And I can do the same thing for the second step. So this time I'll take this factor here, write it in front of the scalar product, and I'll also move that factor here, and I just multiply those two together. And that means what I would get is 1 over 3 square root of 2 times 1 over 3 square root of 2, so it's just that factor squared. Right, times 1, 0, 1, minus 1, scalar product with 1, minus 1, 0, 4, times 1, minus 1, 0, 4. All right, so now just go through the computations. Oops. So here we get minus 1 over 2 times that scalar product is 1 plus 0 plus 0 plus 0. And here we get, let's see, 1 over 9 times 2, so that's 1 over 18. And the scalar product is 1 plus 0 minus 4 times 1 minus 104. So we end up with, let's see. So this is minus 1 over 2, 1100. And here we get 1 minus 4, this is minus 3. So we have minus 1 over 18 times minus 3. That means we can factor out the 3. And we get something like, that's a plus, then 1 over 6, if I'm not mistaken. 1 minus 104. Of course, you'll interrupt me whenever I make a mistake. All right, so let's see what I get as a result. So here I have 1, that is 6 over 6 minus 1 over 2. 1 over 2 is 3 over 6, so 6 minus 3 is 3 over 6. And then plus 1 over 6, that would be 4 over 6. Then for the second element, I get 0 minus 1 over 2. 1 over 2 is 3 over 6, so minus 3 over 6 minus 1 over 6 is minus 4 over 6. Then I get 1 minus 0 plus 0, that's just 1. And finally I have minus 1 minus 0 plus 4 over 6. So minus 6 over 6 plus 4 over 6, that is minus 2 over 6. All right. And that means, well, I can divide everything by 2, and I can factor out a 3. Let's just factor out a 6 first. So we get 4 minus 4, 6 minus 2. And then we can simplify that a little. So that's 1 over 3 times 2 minus 2, 3, and minus 1. All right, so that's the result. And I do hope you still agree. Great, so let's normalize that. So now we need to compute the norm of that one. And now I'll take a little shortcut here. So of course, it doesn't really matter whether I normalize this vector or just this vector. Right? Whatever factor is in there will of course change the norm in the end. It should all factor out to the same thing. The result will always be a vector of length 1 in that direction. So if I have a factor here, I can just forget about that for normalization if it complicates things. Right? So I'll just normalize this. So the norm of this vector here, that is, let's see, 2 squared is 4 plus 9 plus 1. So I get 18, and 18 is 2 times 9, so that's 3 square root of 2. So that means my resulting vector is B3. And that is, and remember, I normalized this vector, so now I also have to take this vector and divide by that norm, right? Or you could normalize the whole thing and then divide by the resulting norm. That will just differ by this factor here. Okay, so now I would get 1 over 3 square root of 2 times 2 minus 2, 3 minus 1. And that should be the result that I wrote down as A before, if I didn't mix up anything. Right? So same procedure, just do it twice for different vectors basically. Of course, it gets more and more work as you move on, but it's always the same thing. You just have to pay attention to not making any mistakes. Questions so far? Otherwise, let me maybe take a quick look at Tweetback. Yeah, I think I did explain how I took out the factor. And by the way, it's Gram-Schmidt. It's not Graham-Schmidt. It doesn't have to do anything with graham crackers. In fact, the mathematician, let me quickly see about that. So it's named after two mathematicians. One is Erhard Schmidt, but you wrote that one correctly. So the other one is this guy here, Danish mathematician by the name of Gram. So that's where the name comes from. All right. I think that's most of the questions that I can cover so far. Good. Any questions from the audience before we move on? Good. So next point on my list is take a look at the homework. So here we have 8.1 and 8.2. For 8.1, we're basically doing the same thing we just did in this example, just a little easier because we only have two vectors. So I'm asking you to determine the orthonormal base of U, and U is spanned by those two vectors V1 and V2. I do hope you all got the correct solution, but let me just ask for that. So here's a quick tweet back again. Do you think you got the right solution? And of course, I'll tell you what that right solution should have been. Just take 30 more seconds. And if you didn't even try, feel free to vote no. That looks surprisingly good. All right. So results should be available in a couple of seconds. Some of my network is slow today. Maybe the will show up at some point. So to cut it short, most of you voted yes, they solved the problem. So let me just give you the right solution to double check. What you should get if you actually started in the order that, here it is. You used the vectors in the order that I gave them to you. You should get something like 1 over square root of 6, 2, 1, 1, 0. And you see the direction of the first vector is preserved, right? And then the other one should be 1 over 3 square root of 2, 2 minus 1 minus 3, 2. Right? And of course, there are multiple methods to write this factor here, depending on what you factored out and what you didn't factor out, but at least this direction should be right. Yeah, so you should get a multiple of that. Okay, so that is U. The question does continue, and I just want to say a few words about that because that has been asked a couple of times. It also asks for a basis of the orthogonal complement of U. And I'll extend that question to say I want a orthonormal base of that orthogonal complement, if possible. So what I need to do to obtain that is basically I have my surrounding space that is R to the 4. And we know that each vector in R to the 4 can be decomposed into one part in U and one part in U ortho, right? The parts in U we know. Those are the vectors spanned by these two. Right? That's the basis for U. So now we need to compute a basis of R to the 4 that contains this basis of U and is an O and B. Sorry, it contains this O and B of U above and is itself an O and B. So that means we get 2 more vectors in that basis, and all 4 vectors are orthogonal. That means in particular everything spanned by those 2 additional vectors will be orthogonal to everything spanned by the first 2 vectors, right? So those 2 additional vectors will span U ortho. And that's what we want. And the 2 additional vectors span U orthogonal, and that way we'll get a basis and even an orthonormal base of U orthogonal. Okay, now how do I get that? Well, first I'll have to find an extension of that basis so that I have a basis of R4. That seems a lot of work. So I'll try to cut it short and just take a guess. Let's say I want to add the vector 1, 0, 0, 0. And the unit vector is always a good guess. Maybe that's not the right unit vector, but one of them should probably do, or probably 2 of them should do, right? I can just do that and then try to compute a basis of the space spanned by this vector, and this one that is an O and B. So I can apply Gram-Schmidt's method to those 3 vectors. First one are already orthogonal, nothing to do about those, so I just have to do the Gram-Schmidt step for this one here. 2 possibilities. I either get a vector that is orthogonal to the first 2. That means I have 1 additional vector, and then I'll just do the same thing for the next one. Or, and now my question is, what happens if this vector, by chance, already lies in U? Let's say this is contained in U, and I just apply Gram-Schmidt's method without knowing that. What will happen? Any guess? Yes. I get a multiple of these 2 vectors. Any other guess? Maybe the 0 vector? No? Not the 0 vector? Okay. Anything else? Yeah. The same vector, so you say I'm getting this one back? Maybe. So you say I'm getting a multiple of those two first vectors, right? So something that is in U, but not necessarily this vector here. You say I get exactly this vector. And I'm still missing the right answer. We get a vector from the span, so from that one here, technically yes. Which vector? It's a very special one. The zero vector, exactly. Yeah, so that is what will happen. Remember, what do I do with Gram-Schmidt's method? I compute a projection of my new vector onto that space, and then I subtract it from my original vector. Well, if that vector happens to be in that space, what is the projection of that vector on that space? It's exactly the same vector. Now I subtract that from itself, so I get the zero vector. Okay? So point is, oops. Point is, I can just do that, give it a try, and if it works, I'll get an orthogonal vector. If it doesn't work, I get the zero vector. And that's a clear indication that the vector I started with is already contained in the space I have so far, right? So I don't even need a basis to start with. Of course, it's easier if I have that because I won't do any unnecessary steps. But if I start with too many vectors, that's fine. The zero vectors will filter themselves out. I can just forget about those and continue. Yeah, so that's totally okay. So what I could do is I could just add all of those vectors. And then I can continue my Gram-Schmidt method. Until we have two additional non-zero vectors. And the zero vectors that we encounter on the way, we just throw those away. Forget about them, go on to the next vector. Yeah? So you may need to do a little more work, but you don't have to think about it. And that might also be valuable. Okay, just wanting to mention that. That means we have a quarter of an hour left. Which leaves us with two choices, I guess. So we could either talk about A2, or we could quickly go over the rest of that chapter. And maybe it's a good idea to at least skip over the rest briefly. We can always talk about A2 next week if you want that. Feel free to add some feedback to the feedback chat wall if you'd like me to discuss that question as well. All right, so that was Gram-Schmidt's method. Let's go on with one of the points that I used for motivation of the scalar product. And that is, I said the scalar product can be used to compute angles between vectors. And we haven't done a lot of angles up to that point, with the exception of orthogonals. So here's how this angles stuff will work. You do remember, hopefully, the definition of the sine and the cosine function from school. Usually it's defined this way. You have a unit circle. This is part of the unit circle. You have a point on that unit circle, call that x here, or the corresponding vector points to this. And you have the angle between that and your x1 axis. And then the sine and the cosine of that angle are defined by this triangle that is spanned here. So the cosine is this value here, and the sine is this value here. Yeah, or here. And of course, what you can see here is this cosine here. That is exactly the projection of that vector onto this line. And that's a relation to scalar products. Basically, that's it, right? So the cosine is the length, to be precise, of that projection onto that line. And the sine, if you want to extend that as well, is then the projection of that vector onto this line. You can do that for the sine as well. And this gives us a way to compute angles, namely through the cosine. So what we do is, let me just skip to that formula. What we do is we compute that projection here. That is the length of this projection. Remember, we need to use normalized vectors for that. So if x and y are not normalized, we normalize them. That's where this comes from. We compute the scalar product. So this is a projection of one vector onto the other. And the length of that projection is exactly the cosine of the angle between those two. And that's it. Right? So if you want to know the angle, you compute that. You project one vector onto the other, and you have the cosine. So you just need to invert the cosine. Okay, and also just a quick note. You will remember the Cauchy-Schwarz inequality, hopefully. That told you something about the relation of those. So what the Cauchy-Schwarz inequality did was it told you that the scalar product of x and y is less or equal to the product of the norms of those two. And that means this expression here is automatically between -1 and 1. Right? So it all works out nicely because the cosine should be between -1 and 1. Okay, and that's how we can compute angles. Basically, that's it, whole story. Not all fully complex, I hope. So let's move on to something more interesting. Least squares. So that's one other application of that whole projection idea, least squares method. The problem is this. Let's maybe skip over that. Say you have data that's coming from somewhere. In this example, what I used was, I think I used interest rates and credit consumption, right? So RI was the current interest rate, and CI was the credit consumption taken out at that interest rate. And of course, you can measure both, right? The interest rate is published by the banks, and the credit consumption can also easily be seen that way. And I'll say we have an idea about how those are related, right? And our idea is there is a relation like this, saying that the credit that is taken out by people depends basically linearly on the interest rate, and then maybe there is some beta to shift it. And the question is, can we verify that this is true? And if it is true, can we find those parameters, those alpha and beta parameters? So how exactly is that dependence? How can we model that? And of course, we can take a couple of measurements. Each measurement gives us an equation like this, if actually this relation is true. So we can just collect enough measurements so we get a system of linear equations. Actually, we have two parameters, so two measurements should be fine. We solve that, we get the values for alpha and beta. Problem here is, of course, that usually this relation might not be quite exactly true, right? Maybe it's approximately correct, but probably not exactly. And if you have something like a law of physics behind that, then maybe that law is correct, but your measurements are not. Yeah, you usually make some minor measurement errors, so the values that you actually obtain are a little off. And that means if you just collect two of those, then you get values for alpha and beta, and if you collect other data points, then you get completely different values. And that's not good. You don't want that, right? Also, if you collect more than two data points, then probably you end up with a system that can't be solved anymore. And again, you don't want that. So what we have here is the problem of having a system of linear equations, much, much more than we actually need, that is infeasible. But we want a solution that is at least close, right? So we want to, in other words, we want to modify the system such that it becomes feasible again. You want the modification to be as small as possible. And that's what we are doing here. So what we have is a linear system of that form, some matrix times x equals b. That is infeasible. We want to make it feasible by changing the right-hand side. So instead of b, we want some b hat here. And we want that change to be as small as possible, but as large as necessary. In more abstract words, this b here is not in the column space of A, right? If it was, then we could find a solution. So we want to find a b hat that is in the column space of A, and that is close, and by close I mean the difference of b and b hat should be as small as possible. We want to minimize that. And as it turns out, what we have to do here is this b hat is actually the projection of b onto the column space of A. Right? That's the best that we can get. That will guarantee that we get a b hat that actually is in that column space, and it will be as close as possible to b. So the idea is, if we have a system like that, we just compute the orthogonal projection of b onto the column space of A. Then we can solve that system, and then we can determine our parameters. And that will give us a solution that is as close as possible to all the points. Yeah? So in this case, we have something like measurements, right? So let's say this is the interest rate, this is the credit consumption, and probably if the interest rate grows, credit consumption goes down. So our data points will be somewhere here, and here, and here, and here, and here. Maybe those are the data points that we have. And the alpha and beta parameters that we get correspond to a line that will be close to those data points. So we get something like that. And of course, the errors that we make can easily be measured by those error bars here, right? So for each point, we make a small error. And by using this method, the sum of these errors is minimized. So basically, you want to find the line that minimizes the sum of errors to all the points that we have. Because there is no line that just goes through all the points. Because if there is such a line, we would get that. If there isn't, we'd at least get a minimizer. Right? And that's what we want to do here. And that method is called the least squares method, or a linear fit least squares method. And of course, that's not limited to functions, linear functions with two parameters. We can also use other functions, quadratic functions, cubic functions, exponential functions, whatever you like, as long as you have a set of parameters that you want to determine and sufficiently many measurements, then you can use this method to determine your parameters. And the way to do that is actually pretty easy. Takes some thinking to get there, but let me just give you the final result. You can go through that thinking to get there in the videos. What you need to do is you need to compute A transpose A and then solve this equation here. And that'll give you your x hat. X is the set of parameters that you're looking for. So that's the set of parameters you want. And your corrected right-hand side, your actual projection will then be A times x hat. Right? So this way you will automatically get the correct solution. Here's a quick example. Say we have this matrix and this right-hand side. And if we just try to solve that system, we find it's not feasible, so there's no solution. So we want to determine least square solution, and we do that by solving this system instead. And basically, I just need to do the computations here. I compute A transpose A, I compute A transpose B, that's my new right-hand side, and then I solve A transpose A x hat equals B hat, equals A transpose B. That's what I'm doing here. And I get this solution. And this is then called the least squares solution. Right? So if our matrix A, or the system that I started with, is one that describes the relation that I want, depending on the parameters, I'll get the correct parameters as a solution here. And this solution will, as I said, minimize the error that I make with that solution. Okay, so that's least squares. There's also a homework problem on least squares, I think. Did I put that on the sheet? Oh no, I didn't. So I'll give you that next time. All right, so we'll see an example for that least squares problem next time. And if you want, we can also discuss 8.2. Just let me know in the tweetback comments if you want to do that. Remember, no lesson this Thursday. Instead, we'll continue next Monday, and the exercise classes for this week will also be next Thursday. So have a nice free Thursday.